Hello, we are from Team Ultro 10539, and this is our control award submission for the New York City FTC Championships.
Our robot is composed of many technical features, one of them being our object detection algorithm. Due to the starting stack being randomized at the beginning of every match, we realized that we needed to have a robust algorithm that would be able to automatically determine the number of rings in a starting stack. To do this, we run an OpenCV-based object detection pipeline. We do this by converting each frame of our video stream into a matrix of values. We then convert our video stream into a YCRCB color format. YCRCB is helpful towards our goal of identifying how many rings there are because it gauges the intensity of red within the image. We also place two sub-matrices on top of each other into our video frame that we specifically analyze. We then determine the total number of rings by determining the mean of the values within the sub-matrices. If the means of the values within both sub-matrices are high, we determine that there are 4 rings in front of our robot. If the values in the bottom matrix are highly intense, we determine that there is 1 ring in front of our robot. If the values in either matrix are not highly intense, we determine that there are no rings in front of our robot.
In the past, our programmers were forced to input random values in our driving functions until the robot would go to the location that we wanted it to go. In this year's competition, we decided to have a more accurate and precise way of navigating during the autonomous period. To do this, our robot boasts a robust localization system. We chose to install physical odometry pods on our robot, which are simply freely spinning omni wheels connected to an encoder that measure the distance our robot travels. There are 2 of them on our robot, one that measures the distance the robot drives in line with its wheels, the y-axis, and another that measures the distance the robot drives while strafing, in the x-axis. This allows us to map the field as a second quadrant in a Cartesian coordinate plane. If the robot drives to the left, there is a negative x value. If the robot drives forward, there is a positive y value, and vice versa for both axes. Using this coordinate system, it is possible for a robot to travel to specific locations on the field with an accuracy of plus or minus 5 centimeters.
Our driver-controlled periods also feature many enhancements. Our drivers have the ability to directly control the speed of our flywheel. This helps prevent any motor damage and gauge the speed at which a ring may need to go at in order to reach the high goal target.
Our drivers also have the ability to adjust which side of the robot is the front of our robot. This is important because we want to make sure that our drivers, some of which have different preferences than others, feel as comfortable and as efficient as possible when controlling the robot. If the left bumper on the first gamepad is pressed, the side of the robot becomes the front of the robot. If the right bumper on the first gamepad is pressed, the front of the robot becomes the front of the robot once again. Our driver-controlled periods also have an automatic flywheel shooting system. With the press of the left bumper on the second gamepad, the robot will go through various functions needed to push the rings up from our bucket, release them from their locked position, and push them onto the flywheel for the driver to choose when to shoot the rings. Thanks for watching.